Visit us on the web at nilfisku.com. Nilfisk University is the cleaning equipment industry's most comprehensive web-based training and interactive learning resource. Your degree in success is just a click away at Nilfisk University.
This lesson is brought to you by Nilfisk University, where excellence is attained through active learning. Hi, welcome to Battery Technology Basics. My name is Leanne Wallace and I'll be your presenter today. Have you ever spoken with a battery salesperson and thought they were speaking a different language? Well, the purpose of this module is to explain for you the deep cycle battery market by defining and comparing the deep cycle battery types available for robust applications such as floor machines. So, the leading technology that we're covering today is the proven technology of lead-acid batteries. Now, not all lead-acid batteries are created equal. So what we're going to do is we're going to dive into 5 deep cycle battery types that you find in the market today. And by going through the actual construction variables that these technologies have, we'll be able to have a better understanding of how the technologies compare. When you look at a battery, in most cases, you see a plastic case or black box. What is inside the battery is what we're looking at in this module, because when you buy a battery, you need to know how the internal components and design of that battery are going to affect your performance and ensure that your equipment requirements match your battery technology. By taking the puzzle pieces of battery construction and fitting them together for you, you can relate how battery construction ties to performance, but also to other important factors like health and safety considerations and environmental sustainability. By grasping the basics of battery technology from this module, you will know 1. How to select the right technology for your equipment. 2. You will have fewer battery problems. And 3. You will gain greater knowledge of battery performance. After successfully completing this lesson, each learner will be able to understand basic battery terminology as it relates to the deep cycle battery market, define the 5 main types of deep cycle battery technologies used in floor care equipment, understand the 4 main construction differences between deep cycle battery types, understand how active material composition used in battery design affects the longevity of a battery, identify which deep cycle battery types are most expensive to maintain, identify at least 3 benefits of valve-regulated lead-acid or sealed batteries and EV traction battery technologies. Identify 3 deep cycle battery types that are certified for environmentally sensitive areas. Let's get started. Here's a review of today's content. In Section 1, Battery Construction Components, we'll cover the basic battery construction components that determine battery performance and life for deep cycle battery applications. Section 2, Battery Construction and Technologies. In this section, we'll spend some time understanding the 5 types of batteries used in floor machines and have a look at the advantages and disadvantages of each. Section 3, we'll do a technology comparison. We'll look at the factors to consider when choosing the best battery technology for your deep cycle power requirements. Once we complete these 3 sections, there will be a review of the course outcomes and a short quiz will follow. Let's look at the basic construction components that interact within a battery so you can understand how they are constructed using this diagram. First off is a terminal. A battery is essentially a can full of elements and chemicals that produces electrons. So if you look at any battery, you'll notice it has 2 terminals. One terminal is marked positive, while the other one is marked negative. Electrons collect on the negative plates of a battery. If you connect a wire between the negative and positive terminals, the electrons will flow from the negative to the positive terminal. Inside the battery itself, a chemical reaction produces the electrons. The speed of electron production by this chemical reaction controls how many electrons can flow between the terminals. Electrons flow from the battery to your equipment and must travel from the negative to the positive terminal for the chemical reaction to take place. That is why a battery can sit on a shelf for a year and still have plenty of power. Unless electrons are flowing from the negative to the positive terminal, the chemical reaction does not take place. Once you connect a wire, you create a path for the electrons to flow and the reaction starts. That's just a quick reminder of how a lead-acid battery works. The next construction component is the plates or grids. Next on the diagram are the white material between the plates, and these are called separators. So these can be made of rubber in a flooded and gel type battery and are made of a glass mat material in AGM, gel Dryfit, and traction dry cell types. We'll talk more about plates and separators later on in the presentation. Next up are these little circles that you see across the top of the battery. These circles will represent the watering fill caps in a flooded lead acid type battery and the safety relief valves in a valve regulated sealed battery type. So again, we're using one diagram here to describe 5 different technologies. So in a flooded application, those caps would be removable for the servicing of the battery, but in a VRLA category type battery, those are actual safety relief valves that cannot be removed. The next item I'm going to point out here are the intercell connectors. And again, that's that circular metal piece you're seeing that's connecting the plates together. And finally, here's the case. So what you'll notice about the case is that it's divided into sections or cells. Plates and separators are grouped together and placed within these cells when a battery is constructed. Once all the components are secured within the battery case, the electrolyte is added. Electrolyte can be liquid or gel and surrounds the plates. So now let's dive into more detail on the active materials. In the basic battery concepts I just covered, you heard me refer to plates. This is the first of 4 basic components that we're covering today that determine battery performance in life. Plates or grids form the lead basic framework within a battery and are either positive or negative. Deep cycle batteries use thicker plates that allow them to tolerate deep discharges better. Plates are made up primarily of lead in deep cycle flooded lead acid batteries and more durable materials like lead calcium alloy in deep cycle valve regulated lead acid and traction type batteries. Reducing the amount of lead antimony, or replacing that with calcium, reduces both the battery's internal heat and amount of gassing that occurs during charging. Since heat and gassing are principal reasons for battery water loss, these differences in plate construction ensure that valve-regulated lead acid and EV traction type batteries do not off-gas under proper charging conditions. In a starter battery, the battery has many thin plates in parallel to achieve a low resistance and high surface area. Basically, a starter battery does not allow deep cycling. A deep cycle battery, on the other hand, has thick plates for improved cycling abilities. A deep cycle battery generally allows upwards of 500 cycles. The total number of cycles depends on the depth of discharge of each cycle. Here's what you need to know about plates. Plates can be thicker or thinner. Thicker plates will increase battery life and deep cycling ability. Thicker plates are found in true deep cycle battery construction. Thinner plates are designed for short burst high current applications such as automotive or UPS applications. Thinner plates are less expensive. The second main component that's important to understand in battery construction is the paste or active material adhered to the plate, basically filling in the grid structure with active material. So active material paste can be more dense or less dense depending on the battery type and the manufacturer. Increased density provides a battery that's more robust, has higher discharge runtime, and longer life. A battery with decreased or lower density in the active material creates a battery that has high initial capacity, such as a starter battery application, but shorter life. In the floor machine application, a more dense active material is required. So now that you have your grid and your active material is adhered to the grid, you need to install an active paste material separator. So basically a separator is a porous sheet that allows transfer of ions between the plates but prevents physical contact, because what would happen is your positive plate and your negative plate, if they were to touch, would quickly transfer ions between them, canceling each other out and lose their stored energy. So in this diagram that's showing you a grid, the actual pasted grid is represented in the light gray. The orange represents your active material. And then this dark gray material at the bottom here is representing what your separator might look like. So again, the separator is going to cover the entire plate, but for the purpose of this diagram, we've used a cutaway. The third component in battery construction when comparing deep cycle battery technology is the electrolyte composition, or basically your electrolyte acid to water ratio. So electrolyte is a liquid substance that acts as a medium to conduct electricity. The specific gravity of electrolyte can be higher or lower. Lower specific gravity of electrolyte generates less heat. Higher acid in electrolyte results in more power and shorter life. Low acid ratios result in reduced heat and longer life. The fourth and final major construction component that affects the deep cycling life of a battery is the electrolyte volume to active material ratio. So batteries in general can have more electrolyte volume to active material or less electrolyte volume to active material, or you'll hear a term acid starved. That is to say that enough electrolyte is in the battery to create a reaction, but you're not completely immersing the plate in electrolyte, such as in a flooded battery. So the term acid starved can only apply to sealed deep cycle technology where the electrolyte is not in a pure liquid state or it's immobilized. So when batteries are under load or being charged, they create heat. This heat destroys the battery because it causes the plate shedding. So when active material breaks down and becomes separated from the grid, gassing occurs and the liquid comes out of the electrolyte, creating a higher acid ratio in the electrolyte, as we discussed on the last slide. So higher electrolyte volume to active material ratios creates shorter life, longer initial runtime, and faster plate breakdown and shedding. In situations of lower electrolyte volume, or when a battery is constructed with a plate preservation strategy of using a less electrolyte volume to active material, what you see is longer life, consistent runtime over the life of the battery, and better plate preservation. So by now you should know some differences between a starting battery and a deep cycle battery. You should also have a good understanding of the major construction components of battery construction that define a deep cycle battery and how these components affect things like cycle capacity. To remind you, we discussed plate thickness and active material densities, as well as performance. And to remind you, we discussed how a thick plate technology with a more dense active material ratio can be deeply cycled for more cycles, provided the electrolyte acid ratio and volumes are controlled. Also, we discussed how construction components affect life. So to remind you, we discussed how plate shedding and increased heat issues are related to higher acid ratios and higher electrolyte volumes. Now let's look at how these components differ in 5 types of lead-acid battery technology. In the next section, we're going to look at the advantages and disadvantages of the 5 main types of deep cycle batteries used in floor machines. These types are flooded lead acid, sealed gel, AGM, or you may hear the term advanced AGM used in the market, traction gel Dryfit, and EV traction. So let's get started with section 2. So here's the cutaway diagram you saw at the beginning. What I'm going to do is point out a couple of construction differences used in flooded lead acid technology and show how these features contribute to product advantages and disadvantages. So first off, a flooded lead acid battery is an electrical storage device that uses a reversible chemical reaction to store energy. It uses a combination of lead plates or grids and a liquid electrolyte consisting of diluted sulfuric acid to convert electrical energy into chemical energy and back again. The electrolyte of a lead-acid battery is hazardous and can produce burns and damage to equipment and facilities. Here are the components of the flooded lead-acid battery that you should understand. First off, the watering fill caps. An unsealed battery gradually loses water due to its conversion into hydrogen and oxygen. These gases escape into the atmosphere through the vent caps. If the lost water is not replaced, the level of electrolyte falls below the top of the plates. This results in high concentrations of sulfuric acid in the electrolyte and causes the plates to harden. The next feature you need to understand about the flooded lead-acid battery is that it's typically made with a thin plate construction. Also, the liquid electrolyte is where the product gets its flooded name from. The electrolyte is in a full liquid state, and therefore the product has ongoing required maintenance and is also considered hazardous technology. So what are the advantages of the flooded lead-acid technology? First off, they have low initial cost and are widely available. There are far more disadvantages to consider when choosing this technology for a floor machine application. Flooded lead acid is hazardous flooded technology. It contains liquid sulfuric acid solutions with removable watering fill caps for servicing. Flooded lead acid, due to their internal chemical reactions and heating during charging, inherently lose water that must be replaced through regular maintenance or damage to the batteries will occur. Flooded lead acid produces off-gassing, which results in corrosion and acid damage to equipment, surroundings, and potential personal injury. Flooded lead acid requires caution and venting to minimize health and safety issues during charging and maintenance. And flooded lead acid has a high cost for storage, hazmat shipping, and handling regulations. Now, flooded lead acid is not maintenance-free, and it should last as long as a traction-type battery, but often doesn't due to its required maintenance schedules to achieve life expectancy. This technology has the highest cost to own when maintenance and premature failure replacement are factored in. So the second technology we're going to look at today is the sealed gel lead acid. And here's a couple of the construction characteristics of this product. So first off, safety relief valves in case of overcharging. This is the first of the next 4 technologies that we're going to cover that fit into the maintenance-free or sealed valve-regulated lead acid category. In a gel lead acid product, typically a thinner plate is used. The major difference in a sealed gel lead acid battery is that the electrolyte has been gelled, and this is where the product gets its name. So the major technological difference between gel and other deep cycle technologies is that gelled batteries or gel cells contain acid that's been gelled by the addition of silica gel. So basically what this does is turn the acid into a solid mass that looks like gooey jello. So compared to flooded lead acid batteries, there's many advantages of the VRLA category that gel cells fit into. So since the battery is designed to be recumbent and eliminate the emission of gases on usage or overcharge, things like room ventilation requirements are reduced and no acid fume is emitted during normal operation. There's also no need nor possibility to check the level of electrolyte or to top up water due to loss of electrolyte. This also reduces your inspection and maintenance. So compared to flooded batteries, gel batteries are more sensitive to high temperature environments and more vulnerable to things like thermal runaway during abusive charging conditions. One of the major issues in gel batteries is they cannot be fast charged on a conventional charger. If they are, permanent damage results. So basically what happens if the battery is overcharged is that voids develop in the gel. These voids never heal because the electrolyte is immobilized. So once you create a void in the electrolyte, you have in effect reduced the battery capacity. So let's have a look at the advantages of deep cycle gel. This product fits into the sealed valve-regulated lead acid category and therefore is non-spillable and maintenance-free. This results in minimal health and safety requirements and can be shipped as non-hazardous goods. Some of the disadvantages of deep cycle gel. Gel is only available in limited footprints. Gel has reduced life due to thinner plates. Gel has increased charging time issues and costs. And gel has high potential off-gassing due to low recombination voltages required for charging. Gel has reduced capacity, runtimes, and performance due to less overall active material. So when looking at this product, it actually has a higher cost to own when performance and capacity, things like runtime and life, are factored in. The third technology we're going to look at today is the sealed AGM lead acid. Here's a couple of the construction characteristics unique to this product. First off, it has the safety relief valves because it fits into the category of being a valve-regulated lead acid battery. It means it's maintenance-free, non-spillable, and no top-up of electrolyte is required or possible. The next item you'll find in a sealed AGM lead acid battery is typically a thinner plate technology. The glass mat separators are a diaper-like material that's fit between the plates, and it's the combination of these glass mat separators and the electrolyte that's absorbed into them that gives the product its name. So AGM stands for absorbed glass mat. So the main difference between the flooded lead acid battery and the sealed AGM battery is that the AGM battery has immobilized electrolyte. So whereas a flooded battery can break open and leak sulfuric acid everywhere, the sealed AGM product is basically non-spillable. So the major difference between the gelled product and the sealed AGM lead acid is how the electrolyte is immobilized. And so the technologies of gel and AGM are very similar from a thin plate construction factor. However, the electrolyte in an absorbed glass mat situation is actually saturated into the pad. And so basically what this means is that if you were to overcharge this product and create a dry spot on the mat, that there's a wicking action in that glass mat material that's going to ensure the battery can recover from this a little bit, and you're not going to be creating those voids in electrolyte, reducing the capacity of this product. Overall, the electrolyte composition will change, but because of the wicking action of the glass mat separator, this product has an advantage over gel when it comes to charging situations. So here's a summary of the advantages of the AGM product. First off, it fits into the sealed VRLA category, which means it's non-spillable and maintenance-free. This means minimal health and safety requirements, and it can be shipped as non-hazardous goods. This product is also widely available. It has low self-discharge rates, being a recumbent technology. Some of the disadvantages of the advanced AGM include reduced life due to thinner plates, reduced life due to reduced active material density, and reduced life due to higher active material to acid ratio. Also, AGM grids, being a thinner plate technology, cannot withstand being repeatedly cycled to depth of discharges greater than 50%. This product overall has a higher cost to own when your performance and capacity, things like runtime and life, are factored in. The fourth product we're going to look at today is the Traction Gel Dryfit. Here's a couple of the construction characteristics of this product. So first off, it fits into the VRLA category, which makes it maintenance-free. This product is constructed with a thicker plate technology. Gelled electrolyte is used in a Traction Gel Dryfit. So basically the Traction Gel Dryfit batteries are using the same construction idea as regular gel, but with the advantages of a thicker plate technology resulting in a high rate long discharge capability. So the Traction Gel Dryfit immobilizes the electrolyte with the same technology as regular gel by gelling it with silica gel. Compared with the flooded lead acid cell, gel batteries offer maintenance-free and health and safety advantages. The issue with Traction Gel Dryfit when using this technology in a deep cycling application is that it requires charging at slower rates. And if you recall from the gel cell, the major issue with gel is how it's charged and how charging abuse can result in reduced capacity. So with the regular gel cell, I explained how you can create voids in the electrolyte by overcharging or not charging this product properly. Well, the same issue applies to a Traction Gel Dryfit. With a thicker plate technology, also this product is a more expensive technology that's available. So once you factor in the charging time and charging issues and the initial cost to own of this product, it's actually one of the more expensive technologies available. So let's look at the advantages of the Traction Gel Dryfit. It's in the sealed VRLA category, therefore it's non-spillable and maintenance-free and has minimal health and safety requirements, and also can be shipped as non-hazardous goods. This technology is constructed with thicker plate technology for deep cyclability, providing longer runtimes and longer life. Here are the disadvantages of the sealed Traction Gel Dryfit. It's only available in limited footprints, and the Traction Gel Dryfit has increased charging time issues and cost. Traction Gel Dryfit has high potential off-gassing due to the low recombination voltages required for charging, and has the highest cost to own when initial cost and increased charge time costs are factored in. So now let's have a look at the fifth and final battery technology that's contained in this presentation. So first off, a definition of an EV traction dry cell. This product fits into the VRLA category, which means it's valve-regulated lead-acid technology. However, its name comes from a thicker plate technology, so let's have a look at that. It has safety relief valves in case of overcharging, and it has a thicker plate construction, which means it has more active material contained within a thicker plate for deep cycling ability. The other characteristics of this product that are unique to this technology is that it uses a glass mat separator, much like the AGM product, but it's the combination of these separators and an acid-starved electrolyte that are unique to this technology. So what that means is when this product is constructed, the electrolyte itself has a lower specific gravity, and there's a lower electrolyte ratio to active material. This results in better plate preservation. So let's have a look at the advantages of the EV traction dry cell. Now, because this is the fifth and final technology that we're comparing today, what I will do is show for you how the advantages of this product are similar to some of the other technologies, but also how some of the advantages differ from some of the other technologies that we've looked at earlier in the presentation. So an EV traction dry cell is non-hazardous, non-gassing, and non-spillable. It's approved for environmentally sensitive areas. It safeguards against spill-related injuries and damage and eliminates corrosion due to off-gassing. It also does not require a ventilated charging room. So these are the characteristics that you've heard for all of the VRLA categories. So that includes your gel, AGM, gel Dryfit, and of course EV traction dry cell. Another advantage of the EV traction dry cell is that it's widely available in replacement footprints, and this is an advantage where it differs from your gel products, which are typically not available in all footprints. Also, the EV traction dry cell requires less charging time than a traction gel Dryfit and has less charging issues to the gel technology. It's constructed with thicker plates and has higher density or more active materials, resulting in longer life and increased capacity. This is, of course, compared to your flooded lead acid, your gel, and your AGM products with a thinner plate technology. This product has a lower specific gravity or acid density ratio to active material, resulting in longer life. How longer life is basically achieved is by using these construction composition, you receive better plate preservation and longer life to the product. Overall, the EV traction dry cell has a lower total cost of ownership when maintenance, health and safety, and environmental compliance along with performance are factored in. So if you look at the cost to own of a flooded lead acid battery, the majority of your cost is going to be related to the maintenance of that product. If you look at the total cost of ownership compared to gel or AGM, your performance of those products as compared to the EV traction dry cell are going to be lesser, and therefore you're going to receive a better return on investment for a longer lasting, higher performing battery like an EV traction dry cell or even a traction gel Dryfit. Some of the disadvantages of the EV traction dry cell is that it requires a proprietary charging algorithm. So this could mean that the charger that you have been using in a typical flooded application cannot simply be used for the EV traction dry cell. Most chargers today are temperature compensated chargers with programmable algorithms, so this may or may not be a disadvantage to you. Also, when you look at EV traction dry cell, it has a higher initial cost to own than flooded and AGM and sometimes gel. So from an initial cost to own perspective, it's very comparable to your traction gel Dryfit. However, it has the advantage of charging and widely available footprints over that product. So now that we've reviewed the different construction components of lead acid batteries and had a look at how these construction components compare across the 5 different battery technologies, now we're going to spend a little time comparing how all of these benefits and features come together from a business case perspective. So here's a design feature comparison. What you have here in this table are the 5 battery technologies that we've reviewed earlier across the top, and the design features down the left-hand side. I'm going to go through this fairly quickly, and in general, if the technology receives a green check mark, it is designed for that or has that feature, and if the product gets a red X, it's not designed for that and certainly doesn't adhere to that. So designed for longer run times and designed for high rate, long duration discharges only applies to the EV traction dry cell, the traction gel Dryfit, and longer run times applies to the flooded. If you recall, this is related to the thicker plate technology and electrolyte volumes and ratios. High charge retention rates only apply to the VRLA types. Shorter charge time only applies to the AGM and EV traction dry cell technology. Maintenance required is represented with an ABC approach, A being inspection, B being cleaning, and C being watering. The one to note here, the technology that stands out, is the flooded lead acid technology, which has the highest maintenance requirements. Looking at initial purchase price is represented with a $ ranking across the 5 categories. So your flooded product, again, is widely available and least expensive to purchase. Your lowest cost to own, however, is different and more important to consider. You'll notice that there's only one green check mark here for the EV traction dry cell product, and why this is because its initial purchase price is typically lower than the traction gel Dryfit. And even though the initial purchase price of the EV traction dry cell is higher than flooded and gel and comparable to the AGM product, your overall lowest cost to own is a factor of maintenance-free, robust product plus the initial purchase price, and that is how the EV traction dry cell receives the only check mark in this category. So let's compare health and safety considerations as it relates to the 5 battery technologies. What you'll notice on this table is across the board, we've got a bunch of green check marks for every technology except for flooded. Why that is because the 4 technologies represented in green are all of the sealed valve regulated lead acid category, which is to say that they are non-gassing and non-spillable. They are HVAC compliant, and HVAC stands for heating, ventilation, and air conditioning. Now, why flooded is not compliant there is again due to the off-gassing that occurs during charging. Also, does not require ventilated charging rooms, does not apply to the flooded battery. And safeguards against spill-related injuries and damage. Again, just a visual for you to think about here. If you drop a flooded battery and you crack that case, your liquid sulfuric acid electrolyte is going to leak out all over the place, and this is absolutely going to cause damage to whatever surface it's on, but can potentially cause injury to the person who has to clean that up. If you look at all the other technologies, if you drop one of those batteries, the electrolyte has in effect been immobilized. It's either immobilized into the gel electrolyte and the gel products, or it's immobilized into the glass mat material of the AGM and the EV traction dry cell. And so that's why the flooded does not receive a check mark for safeguards against spill-related injuries and damage, and the sealed valve-regulated lead acid batteries do. So let's compare environmental sustainability factors as it applies to the 5 technologies. Recyclable and made with recycled products. This applies across the board, mostly related to the fact that battery lead is recycled and recyclable. Designed for use in sensitive areas only applies to the sealed valve-regulated products, gel, advanced AGM, traction gel Dryfit, and EV traction dry cell. Exempt from hazmat shipping requirements also applies to these products and does not apply to flooded. Compliant with LEED certification is also the sealed products. The reason that flooded would not be compliant with LEED is that it's not a maintenance-free product, but it also has definite health and safety issues to consider when managing that product. Compliant with Occupational Safety and Health Administration regulations only applies to gel, advanced AGM, traction gel Dryfit, and EV traction dry cell because of their sealed and maintenance-free nature, and delivers maximum maintenance-free life without additional resources. So one of the key takeaways that I hope you take from this module today is the concept of total cost of ownership and how that changes radically if you have a battery of the flooded nature that needs ongoing maintenance. The cost of maintaining that product, as well as the additional resources required to get the life out of that product, mean that your total cost of ownership is much higher than going with a sealed valve regulated lead acid type. Comprehensive design to conserve resources, improve safety, and reduce waste is only checked in green for traction gel Dryfit and EV traction dry cell, and that's directly related to the longevity and the deep cyclability of these 2 products. And so basically these are the industry leading products that are out there that are going to be able to handle the deep cycling capabilities that your equipment requires, and also do so for a longer period of time. So the total life cycle of that product is longer, and that's inherent in the design of the product. So how do you ensure that you make the correct battery selection? Well, floor machine applications require a deep discharge battery technology. Therefore, a thicker plate or traction technology is required. Floor machine applications require higher discharge rates. Therefore, more robust active material densities need to be in the construction of the batteries you select. Floor machines are used in environmentally sensitive areas and require sealed, clean and green battery technology to comply with hazmat, LEED, and OSHA legislation. When looking at the total cost of ownership of floor machine batteries, you must factor in maintenance labor, resources, and related issues, as well as life of product. So traction type maintenance-free technology provides the largest return on your investment. Thank you for participating in Battery Technology Basics. If you have successfully retained the information in this lesson, you'll be able to understand basic battery terminology as it relates to the deep cycle battery market. You'll be able to define the 5 main types of deep cycle battery technologies used in floor care equipment. You'll be able to understand the 4 main construction differences between deep cycle battery types. You will understand how active material composition used in battery design affects the longevity of a battery. You'll be able to identify which deep cycle battery types are most expensive to maintain, and also identify at least 3 benefits of VRLA and EV traction battery technologies. You will also be able to identify at least 3 deep cycle battery types which are certified for environmentally sensitive areas.
Visit us on the web at nilfisku.com. Nilfisk University is the cleaning equipment industry's most comprehensive web-based training and interactive learning resource. Your degree in success is just a click away at Nilfisk University.